So let's have a look at the transversality proposition. So I'm trying to get this mixed norm where I have transversality in my y variables and nothing in my z variables. So the first thing I do is I unwrap some of the multilinearity. So I fix y and I unwrap the multilinearity in z so that this becomes a multilinear thing in y, but a linear thing in z. So that's this estimate. And so that unravels my L2 on K estimate to K L2 estimates. Now, what I'm going to be doing here is instead of taking points in my simultaneous saturation to be just points in Rn, the points that I'm feeding simultaneous saturation are actually going to be integrals. So say I'm in R3 and I'm doing a K is equal to 2 case. So I have my E1 and E2 directions where I have my transversality. And so these are going to be my points. Okay, so I have like Y1, Y2. Now the object that gets fed into the simultaneous saturation result is not the actual value at Y1, Y2. It's an average over the line that runs through Y1, Y2. Okay, so I just use my E3 direction there. And I average it against some test function phi. And this test function phi is chosen so that it gives me back the L2 norm of my extension operator restricted to this curve. So now when I'm considering my simultaneous saturation thing, well, what I'm comparing is not 2 points, but 2 curves. Okay, so I have now 2 curves, 2 straight lines, and I'm comparing their relationship. And so instead of getting directions between points, I have the directions between the lines. So my first E1 tells me that I have to be able to draw a particular direction between these lines. And my second E2 tells me I have to be able to draw another direction between these lines. And of course, you can start to see why you're getting your obstruction here. You can't do this if you have 2 lines running through the XY plane in 3-dimensional case. You can define a direction between them. So that's the idea of what's going on with the simultaneous saturation result here. So you see we're defining these integrals over subspaces and then feeding those into the simultaneous saturation. But otherwise, it's a very similar sort of argument. Okay, so you estimate along one subspace, and so that just gives you your trivial bound. Now you look at decay, and when you look at decay, you can see that you have to be able to find points on the subspace in the correct direction. But now with your loop, as you go around the loop, you don't necessarily have the same point connected up at each point with the next condition. So coming back to this little picture here, so I start off at one point and I connect and I say, all right, yes, I'm good. There is a correct direction between these lines. And then my next thing is I come to any other point on the line, and then I have to go in my other direction. And at this point I say, oh, okay, that's bad. So these points don't have to be the same, but they do have to lie on the same line or on the same subspace. And so that's what this diagram here is getting on about, this left and right points. Okay, so I connect them up, but I don't know to start off with that they are the same points. However, because I'm only moving in this sort of other direction, moving up and down here in E3 doesn't affect the linear independence or dependence of my movement in the E1 and the E2 dimensions. And so this is what really drives this thing, is that the transversality is expressed in the projection onto the E1, E2 plane. And so it really doesn't matter how much I move up and down in E3. I don't change that projection, and therefore I don't change the loop condition. So what we're getting at here, and this is just a full multi-dimensional case, is that effectively when I connect these things up, I can connect the points and I can get some kind of relationship between them. So this is my new relation, which just says effectively that I can connect them up via moving in those Z directions, which are perpendicular to the ones that I know are transverse. So that still gives me that contradiction and still gives me the ability to collapse the loop. Then I just do the same sort of thing again. Okay, I count my points, I put them well separated, and then the simultaneous saturation result gives me control on N, and I feed that back into my estimate to get my LP result. And so that's what gives you this multilinear result. And it's a nice different usage of the simultaneous saturation, and it really brings apart the point that it's expressed in terms of points, but those points needn't actually represent points in Rn as the only thing that they could be. They could be things like integrals, where the value just tells you where you integrate.